Topic of today's lecture overall is how we populate our mechanisms with reaction rate coefficient data. And so I'm going to start looking at a very kind of brief overview of some of the experimental methods that we might use to isolate chemical reactions and to derive rate coefficient data. Then I'm going to briefly talk about theoretical methods, mentioning master equation approaches. And I also want to talk about how we might bring those two approaches together, which might be a way forward to reducing uncertainties in our data sets. So uncertainties is a kind of a theme that I want to run through the week, really. So I'm interested in how we propagate uncertainties through our models, but also, of course, we want to reduce uncertainties in our predictions as far as possible. And combining experimental and modeling data is one way in which we could do that. So the first part of this lecture, I've indebted to Professor Mike Pilling, who's emeritus professor at Leeds, for supplying me with these slides. He's been working on experimental kinetics methods for his entire career, and I was a postdoc in his group before I came to Princeton, actually. So we're still friends, which is good. Oh boy, if we could turn everything on, that would help, wouldn't it? I've got a new pointer. I've got to pull the thing in, that's what I've got to do. I think I've never done this before. All right, here we go. Yeah, it's difficult to read. So what does an ideal measurement system look like? So we're trying to get a rate constant for a single reaction from these systems. Tomorrow I'll talk about methods about how we might use what I would call bulk experiments for validating models, and maybe also even for optimizing mechanisms. So, you know, if you're used to modeling a rapid compression machine or flame speed, then you've got a lot of different reactions going on, and you've got reaction sequences that are interacting. But if we're doing kinetics measurements, the ideal situation is that we only have sensitivity to the one reaction that we want to measure. Now, the problem is that's not always possible, but an ideal measurement system would isolate the individual reaction that we wanted to study. And so what that means really is that there will be no sensitivity to any secondary reactions that might take place between one of our reactants and some products that are formed, or other types of examples we'll look at later. The other ideal circumstance would be that we're going to derive our reaction rate constants at temperatures and pressures that we need to actually simulate our practical devices. And in combustion, unfortunately, that covers a wide range of temperatures and a huge range of pressures, all the way from atmospheric for normal flames, for example, up to very high pressures for engine and gas turbine type applications. And unfortunately, these two things are kind of oppose each other, because if we try to take kinetics measurements at high pressures, we have to work with quite high concentrations, and that means that we've got a higher likelihood of these secondary reactions taking place. And so there are different approaches in measurements. Some approaches will work at low pressures to try and isolate reactions, and others, like the shock tube, for example, are giving us data at really useful conditions, maybe high pressure conditions, but then have to deal with these secondary reactions that might be taking place. Okay, so we'll have a brief overview of these various different techniques. And I guess one of the other points that I want to make today is that these experiments take a long time to do. I'm sure those of you that are involved in experimental work are fully aware of that. And so we can only really conduct experiments over, or not over whole ranges of temperatures and pressures, but we might need data over wide sets of conditions. And one of the points I want to make is that by coupling with theoretical models, by coupling experimental data and the inputs to those theoretical models, then we can find a way to extrapolate to any temperature, pressure, composition conditions that we might need. So first of all, we're going to start with experimental techniques. very briefly, going to look at pulsed laser photolysis, which is the technique that's been mostly used in Leeds chemistry school. Shock tubes, well, if you've been doing Ron Hansen's course in the morning, then you'll know already more than I do about that. Flow tubes for elementary reactions, and one or two static studies of whole systems, but I'll go on to say more about that tomorrow. And then one of the topics that I find very, very interesting in kinetics, which has developed over the last few years, is the topic of multiscale informatics. And that's the process of bringing together experimental data and theoretical calculations to try and constrain our system better and reduce the uncertainties. Okay, so let's start with pulsed laser photolysis. So in this technique, we're mixing a reactant and a precursor in a photolysis cell. And then usually our precursor is there to provide us with a radical usually that we want to look at. So we might be looking at the reaction of that radical with a fuel species, for example. I'm just thinking that maybe fuel plus OH is a common measurement that we might want to do in these kind of systems. And so we're using a precursor, something like hydrogen peroxide or butyl hydroperoxide. And then we're going to photolyze that very rapidly to produce our OH radicals. Then we're going to monitor some kind of signal that relates to our radical, like OH, as a function of time. The pulsed laser photolysis allows us to study quite short reaction times. And we're also working with low concentrations. And as I said, the key here is to try and minimize secondary reactions which may take place. So, for example, if we're working with a transient like H2O2 that we're then using to produce OH, if we've got too high concentrations, then the reaction of OH plus hydrogen peroxide might be sensitive, and that will affect our ability to isolate the reaction of interest. So we're working with low precursor concentrations, a high pulse energy for our laser, and we're also measuring distant from any reactor walls because we don't want the influence of any wall reactions taking place either. So we've got various different detection methods available to us, and these all come with I guess, different advantages and disadvantages. One of the advantages of using absorption spectroscopy is that if we have all the right information, so the absorption cross-section and the path length of our cell, then we can actually back out absolute concentrations using the Lambert Law here. Okay, so that's quite useful because obviously the absolute concentration will help us, and if we monitor that over time, it will help us to back out the rate constant. So in absorption spectroscopy, the light of a frequency which is corresponding to vibrational or electronic absorption of the radical is passed through the cell, and then we watch the decay of that absorption signal. So the Lambert Law, I'm sure you've met that before, is the incident, the signal is related to the incident radiation times the exponential of the absorption coefficient multiplied by the concentration and then the path length. Okay, so we need to monitor voltage change from a photomultiplier and relate that to the light intensity and then hence back out the concentration. Okay, so this is a useful technique because we can actually use it to give us an absolute concentration, but the signal-to-noise ratio is often not great, so it's not the most sensitive technique to use. But sometimes it is necessary to use it. And one of those examples is if we've got a second-order reaction, so C3H5 plus C3H5 here, because the reaction is second-order in the species, then we need to know the absolute concentration of the radical in order to be able to back out the rate constant. So we'll see in a minute that for pseudo first-order rate constants, that's not the case. We can use a different method, even using relative signals. But for second-order reactions, we need the concentration in order to be able to back out the rate constant here. Second detection method then is a more sensitive method, but in this case it's only giving us a relative measure of the concentration. And this is laser-induced fluorescence, or LIF, you'll see in the literature. And so here, what we're doing is exciting, well, we're tuning our probe laser to excite a given energy level jump, and then we're watching for that, we're monitoring the fluorescence as the electron drops back to its ground state. So we usually use a dye laser here to excite the radical to the upper electronic state, and then we're monitoring the fluorescence signal. So we don't really have a way to get the absolute concentration here. We're only looking at the relative measure of the signal relative to the initial signal strength. But we can design this experiment to minimize light scattering and to minimize signal to noise, noise to signal ratios, I suppose. And so it's quite a sensitive technique. So we can detect much lower concentrations using this technique than we can with simple absorption spectroscopy methods that I talked about earlier, down to 10 to the 8 molecules, for example. So the setup would look something like this. So we've got our pulse laser, which is going to photolyze our precursor to give us our radical, something like OH. And then in our cell then, we've got our starting reactant, and we would normally have that at high concentration so that we can kind of assume what I would call a pool chemical approximation. I'm not sure if that's used in this type of kinetics, but what it means is that we're basically going to treat that initial concentration of our reactant as a constant. So there's so much of it that we're not worried about how much of that we're losing in the reaction. So if we take, for example, fuel plus OH, we have low concentration of our radical, which we generate from photolyzing our precursor, and then that's going to react with the fuel molecule, which we assume is in kind of a steady state. Okay, and so we're using a dye laser to give us our fluorescence signal, and then monitoring that signal as a function of time by basically varying the delay between our photolysis pulse and our fluorescence signal. Okay, so that's what I'm saying here. So we set the delay time between the photolysis laser and the probe laser, and then we repeat the experiment with various different delay times. So what we will end up with is a fluorescence signal which hopefully will decay as a first order exponential. Okay, so that's not always the case, but if we've isolated a pseudo first order reaction, then that's what should happen. And so the signal should be proportional to the exponential of minus the pseudo first order rate constant times time. So how then do we actually derive the real rate constant? So the pseudo first order rate constant is basically because we're assuming the poor chemical approximation for our reactant. So in this case, looking at OH plus SO2, so our pseudo first order rate constant is basically the rate constant of interest, which is the rate of this reaction, multiplied by the initial concentration of SO2, which we assume is not going to decay very much over time. So the process is described here. So we're basically using various delay times between our photolysis laser and our fluorescence measurements. And if we do that, then we'll get this pseudo first order decay, which is proportional to the decay in OH through the reaction. Okay, so because this is a first order exponential decay, if we plot the log of that signal against time, we should get a straight line. Okay, and that straight line is the slope of that straight line is basically our pseudo first order rate constant. But that's not the actual rate constant of interest. Okay, so it's equal then to the rate constant of interest multiplied by the concentration of SO2. So in order to back out the rate constant for the reaction, we have to do the experiment at various different starting concentrations for SO2. And then if we plot the pseudo first order rate constant against the initial concentration of SO2, then the gradient will give us the rate constant. Okay, so it's quite a high number of experiments to do in order to derive the rate constant for the reaction. So that all works well if we get a nice first order decay here. Okay, so I guess if you're doing this kind of experiment, what you're looking out for is anything that doesn't look first order, where you might have secondary reactions taking place, and so you've got more than one time scale that are involved in that decay of OH. Okay, so I think the first thing to check from this type of experiment is that you do have a single time scale in this decay profile. Okay, so the literature is full of these types of examples of reactions. I just picked a few out of the slides that I borrowed from Mike. So this is OH plus acetylene. And in this case, we've got a pressure-dependent reaction. And so in actual fact, on top of everything else, you have to repeat the experiment here at various different pressures in order in the end to fit a Troy fall-off type curve. So I guess the point of most of this work is eventually to fit the type of rate constants that we would use in chemical mechanisms. And so either an Arrhenius expression, an extended Arrhenius expression, or Troy fall-off is one example of the pressure-dependent. So this particular experiment has been done at various temperatures and various different concentrations in two different bath gases, nitrogen and helium. Okay, so sometimes then we don't see a single decay curve, and we don't even see a kind of Arrhenius type behavior in our data. So here we've got OH plus acetone, and you can see that the plot of the rate constant versus temperature doesn't look like an Arrhenius, and in fact it looks like we've got activation energies for this reaction of different signs going on. And so we've got potentially something strange going on here. It may be that in this reaction the H abstraction is not the only mechanism, or it may be that the potential energy surface isn't as simple as we first thought. I think there's been a more recent paper which suggests that actually there's a kind of a weak well in the entrance channel to the potential energy surface for this reaction, which gives us this strange temperature dependency in the behavior. So I did mention an example like this yesterday as well. I mean, I guess that for people, for us lot who are using reaction rate constants, again here this is expressed as the sum of two standard Arrhenius expressions. And you can see that there are opposite signs to the activation energy in the two parts of that double expression. So in ChemChin, you declare that as a duplicate reaction, and the overall rate is the sum of those two Arrhenius terms, where you've got two different signs for the activation energy. So in order to be able to use this sort of pseudo first order approach to the analysis, then we need secondary reactions to play a negligible role. And that means that we should keep the initial radical concentration fairly low. So there is some examples of analysis of what might happen if that's not the case. So this is OH plus methane going to the methyl radical plus H2O. And a typical radical decay time in a pulse photolysis experiment like this would be something of the order of 0.1 to 1 millisecond. But actually, we have got the potential for a secondary reaction between OH and the methyl radical. And And the rate constant for that is of the order of 10 to the minus 10 centimeters cubed molecule per second. So that gives us a timescale for the removal of OH by that reaction, which depends, of course, on the concentration of the methyl radical. So it's 0.1 second if we have 10 to the 11 molecules per centimeter cubed of methyl radical. But if we increase that to 10 to the 13, then it becomes a millisecond, which is similar to the order of the decay of OH. So what that means is if we have too high a concentration, then we're likely to run into the influence of this secondary reaction that we're not trying to measure. So what it would mean is that we then have to invoke some kind of chemical mechanism in order to be able to get the rate constant that we're interested in. And the uncertainties in that mechanism will feed into the uncertainties in our rate constant. So the trick is, I guess, then to avoid concentrations that will make the system sensitive to that secondary reaction. Okay, so we do that by keeping the amount of OH generated quite low and also working at quite low pressures. So what that means is that really we're doing experiments at pressures which are much lower than we want to use the rate constant, and maybe even a different temperature regime than we want to use the rate constant. So it poses the question: is it useful to do experiments below 500 Kelvin, for example, and well below 1 atmosphere to give us rate constants that we're going to use to model a gas turbine? Oh, you see it. Okay. People are shaking their heads. Yes, no. So I think what I want to show later on is that actually, well, maybe not surprisingly, but by coupling modeling and experiment together, we can show that actually it is useful. I mean, sometimes we can even fit Arrhenius expressions at low temperatures that are valid at high temperatures. If we've got simple Arrhenius behavior, then we should be able to do that, right? Because the log of the rate constant versus inverse of temperature, it should be a straight line. But when we've got more complex systems, where we've got non-Arrhenius behavior, then doing the experiments over a limited temperature range is not going to give us enough information. So then maybe what we might have to do is couple different techniques together. So, lift type measurements with some shock tube measurements for the same system. But coupling with modeling is one other way to try and resolve that situation. Okay, so that was a little bit of an aside. But so the advantage that we get from doing LIF, even though we are working at low pressures and maybe not combustion temperatures, is that we get a very sensitive detection technique. And so the measurement that we actually take should have a fairly low experimental error. Things have moved on in the field. So actually, we can also now use mass spectrometry as a detection method. Here we're measuring the mass-to-charge ratio of ions, which are typically represented as intensity as a function of the mass-to-charge ratio, so the mass spectrum. So then by comparing against reference spectra, we can get concentration measurements for our species. So ionization is achieved by bombarding the reaction cell with electrons or with photoionization using a high-energy laser. And we can also use time-of-flight analyzers. And what we're doing here is using an electric field to accelerate ions through the detector, and particles with the same charge but with different masses will have different times of flights. And so by measuring signal, we can recognize what species are coming out at different times from our system. So perhaps one of the disadvantages here over LIF. LIF is a non-invasive technique. It's using lasers, so it's optical access, non-sampling method. But time-of-flight methods require sampling. And so I guess the things to point out there is that what we don't want to do in our sampling is change our sample chemically or allow any chemical changes in our sample. As we're doing that, we want to measure what's actually happening in the cell. So that's just something else to watch out for. But the advantage is that we can measure several species simultaneously.
I was not really able to understand why time of flight analyzers are beneficial over like a normal single or triple cohort. Is it because to separate out isotopes?
No, actually, I mean, to separate isotopes, we actually need to tune the light source, so I'm going to come on to that in a minute. Yeah, I mean, basically, with a standard time of flight analyzer, anything with the same mass is going to give you the same signal. So if you want to separate, then we have to use advanced light sources, so something like a synchrotron. And there are big advantages there in recognizing isotopes. I'm not sure what I wanted to say about this. It's just a nice picture, I think, from Mark Blitz of a time of flight system. And it's been used, I mean, you know, been used for many different systems, really. This one example is SO plus NO2. So here we're photolysing precursor to give us, or Cl2 SO to give us our SO. And then we've got our ion counts at different times, which is showing, showing NO, NO2, and SO. And by using a reference spectrum, we can actually get absolute concentrations out for these species. And by looking at different delay times, then we can get our rate constant. So coming to this issue of isotopes, this is a more recent example of how we might use advanced light sources to distinguish isotopes. So in the synchrotron, we've got a tunable light source, so we can tune it to different photon energies. And because of the different photoionization efficiency curves for even species with the same mass, we can distinguish between isomers with the same mass. And so this was actually, I think it was a science paper. So basically, this was the first time that enols were actually measured, I think, within a flame. So that previous to this, they hadn't really been even included in chemical mechanisms as a potential product. We're used to seeing acetaldehyde from oxygenated fuels, but the isomer here, ethanol, hadn't really been included in chemical mechanisms and hadn't really been measured directly in experiments. And so the ability to use a tunable light source allowed the distinction between these two isomers and showed that actually there was quite substantial concentrations of the enol in this flame. Let me remind myself what flame it was. I didn't remind myself. I looked it up this morning and I've forgotten already. What this means is that actually we've now got the opportunity to look at new validation targets for our models as well, because we can actually get species measurements. And I'll talk about this more tomorrow, but the ability to use multiple validation targets to test our mechanisms is actually really useful, because different targets have sensitivities to different reactions within the scheme. And so by utilizing and comparing our model simulations against different targets, we're testing different rates or different reaction rates within the scheme. So there was some similar work done at the Synchrotron Research Lab in China on butanol flames, again identifying enols that hadn't been seen before, so ethanol, for example, here. And again, distinguishing this from acetaldehyde using photoionization as spectra. So well, it's a sampling method, right? So it depends on at what point you've sampled the reaction. And I'm not entirely sure whether or not you would sample sequentially or whether you Does anyone else know this, whether you have to rerun the experiment and sample at different times from different repeats?
You have to.
Yeah.
So you basically have like a multiplication valve box where you have multiple samples. Length of the entire chamber, you have to basically sample all throughout there.
Yeah. Very time consuming. Cavity ring down spectroscopy is probably one of the higher sensitivity techniques. And the reason is because basically of the extensive path length that's in this system. So what we've got here is a cell which has high quality mirrors, or technically it's called a high finesse optical cavity. In its simplest form, that's going to be two highly reflective mirrors. And because we've got reflections back and forth across the mirrors, then we've got an effective path length of the order of a few kilometers. And what that means is that we have a very sensitive technique which we can measure extremely low concentrations. And this is an absorption technique which is used to determine mole fractions down to the parts per trillion level. Okay, so the setup is basically a laser which is illuminating this cell, which is a high finesse optical cavity. Then we set up resonance within the cavity by building up the intensity due to interference of the signal. And then when we turn off the laser, we watch the decaying light intensity leaking from the cavity. And what we do is we measure what's called the ring down time, which is 1 over E of the initial intensity, and that can be used to calculate the concentration of the absorbing substance in the gas mixture if we know the cross-section and we know the length of the cavity. So that's an absolute technique with very high sensitivity. Briefly on shock tubes, because I don't know if you've all been to Ron Hans's this morning. I haven't got too much to say here, but I wanted to say something which I found really helpful actually about the work that comes out of Ron's lab. So probably you all know the basics of what a shock tube is. So we have a high pressure driving gas expanding when the diaphragm opens, and that creates a shock wave. So that gives us a high temperature usually, although the temperature is getting lower all the time, experiment which we monitor near the end wall. So this is, so we can, Ron is, I think, really expanded the conditions now over which shock tube measurements can be taken. So down to 600 Kelvin is getting down now, really overlapping with the region of the rapid compression machine to measure ignition delays and also to measure kinetics. So a very wide range of conditions and a very wide range of pressures. But I suppose the downside here is that we're not working at the low pressures and low concentrations that we would see in a lift-type experiment. And so we are going to see the secondary reactions taking place in this type of system. But what I find nice about the developments in the shock tube area is that actually now the sensitivity analysis is carried out for the system so that you can see what the potential influence of these secondary reactions might be. So this is an example of CH3 plus OH. Okay, so this is the reaction of interest, CH3 plus OH. So in an ideal world, the whole sensitivity of the OH measurements would be related to that reaction. So we would see zero sensitivity from any of the other possible reactions. But in a non-ideal world, we do see some influence of secondary reactions. So CH3 reacting with itself is the highest sensitivity here. But we've got sensitivities from 2 or 3 different secondary cross reactions that take place here. So what that means is that we actually have to model the system. And any errors in these secondary reactions are going to feed through into errors in the reaction rate constant that we're trying to measure. And I think probably if I go back to when I first started using models, I don't think anybody was really doing that, was really looking at that influence of the secondary reactions in a consistent way. But that is happening now in a very consistent way. Okay, what did I want to say? Sorry. Okay, yeah. So this is an example of OH plus formaldehyde. So again, we've got our precursor to produce our OH radicals, which in this case is tert-butyl hydroperoxide. And the shock heating actually will break apart this molecule to give us our OH radicals. And then we have a precursor for our formaldehyde. And then we're looking at the concentration time histories using laser absorption. Okay, so in this case, the rate constant is determined by fitting a detailed model. I don't know if I would choose a GRI mech now since it's 20 years old, but can't have everything. Backing that out, but including a detailed uncertainty analysis, which is the thing that I like about this work. So then a very careful study of what's contributing to the overall uncertainty in the measured rate constant. So the overall uncertainty is estimated to be really quite small, 15%. It's pretty good for a rate constant measurement. And the various different contributions to that overall uncertainty are listed here. You can see that the major factor, which might give us up to about 10% of that error, is coming from the uncertainty in one of these secondary reactions. So in this case, OH plus CH3. So if you assume in the model an uncertainty factor of 2 for this reaction, then that leads to a 10% uncertainty in the rate constant for the OH plus formaldehyde reaction. Okay, and the other uncertainties are to do with experimental measurement uncertainties, so measuring the time at 0, uncertainties in the absorption coefficient, uncertainties in specifying the initial mixture exactly. Okay, so the influence of this secondary reaction is fairly small. So this is the OH sensitivity to these two reaction rates. So as we would wish, the main sensitivity is to the reaction of interest, OH plus formaldehyde, but there is a small influence of this secondary reaction. And that's giving us 10% of the overall uncertainty in the rate constant. Okay, but that is a sort of robust treatment of what's actually happening in the system. And for those of us that are using models, having a detailed assessment of the uncertainty in the data that we're using is extremely useful. So I think I've put this slide in just to show that, well, there are changes in experimental techniques over time, right? So if we plot all available data on, it's not quite an Arrhenius plot, it's on a log scale, so I suppose it is. But so this is basically plotting rate constant over 1,000 over T. So the fit from that shock tube work is the solid line here. And the circles are the measurements from the Stanford shock tube work. But you can see that there are previous fits and there are previous sets of data that don't quite align with the new data. And that will quite often be the case if you plot your Arrhenius fit to all the data that's ever existed, you will find outliers. And so experimental techniques have improved over time, and so potentially the quality of a measurement that was taken in the 1980s will not be as high as the quality of measurement that's taken now. And so we do sometimes see outliers in these plots. Okay, so this is another example, OH plus aldehydes. Again, an absorption technique used. In this case, CO absorption. And again, a detailed uncertainty analysis, including the influence of these secondary reactions. Okay, so in this case, the secondary reactions are towards the bottom of the contributions to the uncertainty. specifying the initial mixture concentration, and the fitting uncertainty are actually higher. But this was a very comprehensive piece of work looking at a range of different aldehydes and their reaction with OH. Okay, we can also, so this is an old example, we can also use flow tube reactors to give us information about rate constants. So in this case, this is a radical plus radical reaction, and these are much more difficult to tackle experimentally, in fact. So I would imagine that the uncertainty from this type of experiment is relatively high. In this case, OH again is generated by pulse photolysis, this time of water. Reaction is taking place with oxygen in excess, and that oxygen has been generated from N plus NO. And the measurement is at fairly low temperatures. This is a much more up-to-date example of a plug flow reactor, where here we're using synchrotron photoionization mass spectrometry for looking at pyrolysis species that are producing the pyrolysis of N-butanol. Okay, so we've got a plug flow reactor here, and then again sampling into mass spectrometer. Okay, and this is giving us quite detailed information on concentrations as a function of temperature from this flow reactor. So that's partly used to back out rate constants, but it could also be used to validate chemical mechanisms. And sensitivity study was also done as part of that, and that's basically just giving us the main reactions which are sensitive in this system. So again, this is not a system which is isolating an individual reaction rate. So just want to now look through some examples from the hydrogen-oxygen system, because obviously we're interested in hydrogen as a future fuel. We might have the thought, well, you know, H2O2, this has been around for a very large number of years. Don't we know this perfectly, this system? Don't we know everything there is to know about this system? Shouldn't we be able to model hydrogen oxidation in a very straightforward way? So let's have a look at the data that we have, some of these reactions. I don't know if anyone's seen this before. Yes, many times. Just to remind you of what the important reactions are and why in the hydrogen-oxygen system. So this is a plot of the explosion limits in the hydrogen oxidation system as a function of pressure and temperature. And I guess it's interesting in terms of reactivity. So as we cross the limit to different temperatures and pressures, we can move from a region where we see no ignition to a region where we see ignition, and then we can move back to no ignition and then back to ignition again. So why is that? We've got these three ignition or explosion limits. In general, the reason why we switch from one regime to another is because we've got this competition between reactions that are chain branching and thus accelerate the rate, and reactions which are termination and thus are slowing down the rate of reaction. And these vary with temperature and pressure. Okay, so at the first limit, we've got the competition between actually a wall termination of hydrogen radicals in competition with the main chain branching reaction in hydrogen-oxygen, which is the reaction of the H radical with oxygen. So this is chain branching because we're going from one radical, H, to two radicals on the right-hand side, OH and O. Okay, so this is accelerating the reaction because these two radicals can then go on to react with other large molecules, hydrogen, for example. Okay, in the second limit, we've got the competition between the chain branching reaction, the main one here, and also the pressure-dependent termination reaction. Okay, so as we increase the pressure, then the rate of this reaction will increase, and that potentially will slow the reaction down and move us back into the no-ignition regime. Okay, so maybe thinking, well, HO2 is a radical. So why is that termination reaction? But in fact, HO2 is a less reactive radical than hydrogen or OH or O. And so effectively, this is a rate-slowing reaction at this temperature and pressure in this regime. But actually, as we move up in temperature or pressure again, then HO2 can react with itself to form hydrogen peroxide. And then as we cross the third limit, we get to temperatures and pressures where we have enough energy to dissociate hydrogen peroxide back to 2OH radicals, which again is increasing the reactivity. Okay, so in the region between the second limit and the third limit, forming HO2 effectively prevents ignition. But as we move to higher temperatures and pressures, then the route through H2O2 to form 2OH radicals is again recommencing propagation and chain branching. Okay, so we've got these various reactions competing, and we've got other reactions involving other intermediates in the hydrogen-oxygen system. So, you know, there's not much. They're small molecules. So how well are we able to do? I might come back to that tomorrow, actually. Just as another preliminary on this, Mike Burke did quite a nice sensitivity analysis for various different experimental targets of the reactions in the hydrogen-oxygen system. There's no major surprises here. We do see some differences between different experimental targets. So included here, we've got burning velocities, which come from flame experiments. We've got ignition delay times, which might come from a rapid compression machine or a shock tube. And we've got hydrogen concentrations in a variable pressure flow reactor. And there are some differences in sensitivity. All of those targets are sensitive to that main chain branching reaction, H plus O2. All of them are sensitive to the main termination reaction, H plus O2 plus M. And then we've got, you know, smaller sensitivities to the other reactions that vary between the different targets. H plus O2 is an important step. That's a radical plus radical reaction, so that one is tricky to measure experimentally. We've got also HO2 plus OH, etc. So that gives us an idea of the reactions that we need to know accurately in order to be able to predict key combustion quantities like flame speeds, ignition delay times, and hydrogen concentrations. So let's start with the main chain branching reaction. H plus O2 goes to OH plus O. So we have some fairly recent shock tube measurements for this reaction, and everything fits fairly nicely on the line. Some of the older data is slightly more scattered, but the more recent data fits nicely on an Arrhenius type expression. And the suggested uncertainty for this reaction is plus or minus 10%, which, to be honest, is about as good as it's going to get for a rate constant. So the general consensus view, which was supported in Mike Burke's paper, is that we know this chain branching reaction to quite high standard of accuracy. O plus OH goes to H plus O2. This is an old plot from one of the Bolsche evaluation studies. You can see there's an awful lot of scatter in the historical experimental data for this reaction. It's been studied over low temperatures, mainly by laser flash photolysis. It's not hugely sensitive in combustion, but actually it's in the mechanism as the reverse of H plus O2, obviously. It might be better to use the most up-to-date thermodynamic information and actually estimate it from the forward rate using the equilibrium constant than base our rates on uncertain experimental measurements, I would say. So I think basically for this reaction, I haven't said it on the slide actually, but we know this H plus O2 very well, within 10%, as I've just said. And through the use of active thermochemical tables, we have very high quality data on the heats of formation for and other thermodynamic parameters for everything in this system, and so we could estimate this reaction rate using the equilibrium constant. Okay, the second branching step, O plus H2. So again, this is branching because we've got one radical on the left forming two radicals on the right. We've got a range of data here, flash photolysis measurements, shock tube measurements that are slightly older, and then more recent shock tube measurements from Davidson and Hansen. I'm not sure if I've put the suggested uncertainty on the slide, but basically there's not too much uncertainty and not too much scatter around the suggested Arrhenius expression for this reaction, so it's fairly well known. H plus O2 plus N, so this is the sort of termination reaction, at least at intermediate temperatures and pressures, converting H into the less reactive HO2. So the reaction is at the third order limit, except at higher pressures. And so I'm not sure we ever reached the high pressure limit experimentally for this reaction. So Michael et al. Have measured this using flash photolysis for a range of third bodies. And actually, it's the third body information for this reaction which is going to be the key source of our uncertainty in this rate. So assuming that's Joe Michael from the Argon group, looked at a range of different third body colliders and which go into the formation of this rate constant. So one of the things which was discovered by that set of experiments was that water was actually a pretty efficient collider. And here we've got basically the temperature dependence of the collision efficiencies for the reaction. But the error bars on the experimental measurements are reasonably large. And I think we're still really discussing how best to represent these types of pressure-dependent reactions, and particularly how we should represent systems where we've got multiple third bodies. So yeah, well, I don't know if it's on a future slide actually, but one of the things I wanted to say was that one of the points I made yesterday, which I reiterate today, is that just using simple sums of efficiencies has been questioned lately, just using simple linear mixture rules for third bodies. And there has been suggestions of using sums based on reduced pressure for these types of systems. Okay, so there have been also high pressure measurements of this reaction using pulse photolysis, a flow reactor. So this is work by Fernandez et al. From 2008, so relatively recent. And you can see then, if we put all that data together, then we can try and fit a fall-off curve. But actually, none of the experimental data quite reaches the high pressure limit for this reaction. So if we want to do this, then that requires calculation of the limiting rate coefficient that we can't access experimentally. So as part of Mike Burke's paper, did a full model evaluation, including at high pressure combustion, for the hydrogen-oxygen system, and updated rate constants for this fall-off using high pressure limit values from high quality ab initio studies from Harding and Troe. And actually also investigated this influence of nonlinear mixing laws. And so, you know, there is, in terms of predicting mass burning rate for hydrogen systems, there is a substantial difference there between using linear mixing rules and non-linear mixing rules for those third body efficiencies. So I think that's a debate that is basically still ongoing. So we're still on the same reaction here. This is a more recent study by Steve Klippenstein et al. And I think the attempt here was to say, like, let's theoretically throw everything at this, the highest quality modeling that we can do, and let's see if it's as good as the best experimental data. So I guess trying to prove that for small molecules at least, theory now can do as well as experimental data. So that involved a multi-reference configuration interaction potential energy surface calculation, so very high level of theory, if anything made sense yesterday, and then coupled with, I haven't talked about this yet, but I'll mention master equation methods later, a 2D master equation method. So that's again, high level simulation of the system, and that gives us a solid black line here. So what they were trying to do is to do this in a completely a priori way and say, right, we're not going to fit anything that goes into our model. We're not going to use experimental data to try and better constrain our potential energy surface, as is commonly done. We're just going to do it completely from theory, a priori. And then also what we've got on here is a fitted master equation result, which is the solid red line. And the solid blue line is fits to that Fernandez high pressure data I just showed you. And basically all of these things are fairly tightly together. And I guess the conclusion, at least Steve's conclusion from the paper, was that for this system, the a priori theory values are within the error bars of the experiment. And so concluding that you can do as well for small molecules like this and a very high level of theory, you can do as well as experiment. But that, of course, is not universally true. Sorry, I just want to see. Okay. Yeah, this is the last slide before the break. Okay, so here we've got a thermal dissociation reaction. So this is the reaction which becomes important at high temperatures and pressures because it's giving us back reactive radicals, 2OHs. The reaction is far from the high pressure limit. And so, again, this was again modeled by Jürgen Troe in this case, and thermodynamics was used to relate the forward and reverse reactions using an updated enthalpy of formation from OH. I don't know, I think that's probably likely to come from active thermochemical tables. Okay, so there could be uncertainties in this reaction. There's also been some shock tube studies, and actually the experimental data and the fitted rate coefficient expression quite tightly bunched together. So that suggests pretty good experimental data for hydrogen peroxide dissociation. Okay, so I think we're probably approaching sort of break time. So I think I'll probably take a short break now, and then after the break I want to introduce you at least to the concept of this multi-scale informatics. Has anyone studied that before or heard of it even? Or no? Okay. Anyway, we'll look at that after the break. So to move on to the brief section on multi-scale informatics, I'm not exactly sure where the name came from, but the multi-scale particularly. But the idea here is basically to combine theoretical modeling with experimental data to try and better constrain systems, particularly for systems where we have discrepancies or we have high uncertainties in our rate constant predictions. And so there's several examples of this type of analysis emerging. I'll probably look at a couple more towards the end of the session today. But this particular one is HO2 plus OH. So I guess you would call this a radical reaction. And the temperature dependence of the rate constant for this reaction has been the subject of quite a lot of debate. And as I mentioned earlier, radical reactions are difficult to study experimentally. So if you look at the symbols on this plot, this is the experimental data. So very strange set of data, really, that looks, at first glance, looks fairly inconsistent, right? So in the experimental data, we've got non-Arrhenius behavior, particularly between the temperatures of 900 and 1300 K. And we've got this quite deep, narrow well with a minimum at low temperatures here. How to resolve the fact that basically if we do theoretical simulations, then we don't see this type of deep well. So how do we bring all this information together? So this is, I guess, one of the early examples of this multi-scale modeling approach, where basically we're using a combination of experimental data and limited conditions coupled with theory. And the idea here is that you use the experimental data to fit parameters within your theoretical model over certain conditions, and then you can use your theoretical model over a wider set of conditions to simulate the rate constant over a wide range of temperatures and pressures. So initially, the theory, without any constraints from experiments, so using only ab initio methods, so for example, by calculating the potential energy surface and then running a master equation model, I'll come to that later, but basically to simulate the rate constant, we see quite large uncertainties, which are the green shaded region here. Okay. Then we say, well, okay, we do have some experimental measurements, and I guess you have to make a judgment about the ones that you want to use in constraining your model. But actually, say that basically we've got uncertainties in things like the barriers, energies of the transition states, for example, or well depths, or maybe frequencies. So uncertainties that are coming from our calculations of the potential energy surface. But actually, we've got some experimental data, and so maybe we can use an optimization method to give us a better constraint on the inputs to our theoretical model. And so the blue is it kind of shaded region here is showing what the system looks like when you constrain the theoretical model using the low temperature data. As you can see, basically the well isn't there, even when we predict all the way up to high temperatures. It does find a minimum rate near 1200 K, although this is quite a lot less pronounced than the experimental data suggests. So on this plot, we've got the whole temperature range. We've got the a priori model, so this is the sort of best estimate from the a priori model, and then the best estimate in the range of uncertainties from the constrained model, which fits quite well the low temperature data and fits through some of the higher temperature data. But you can see that there are quite a lot of experimental data points which are quite a way out of the predicted uncertainty ranges. So I think the conclusion might be that not all of the experimental data is consistent in this particular system. It's an example of HO2 plus HO2. Not quite such a huge amount of scatter in the data here, but we do see quite an interesting temperature dependence for this reaction, and we do see some scatter in the low temperature data here. So Mike Burke's paper suggested that actually it was sort of fairly difficult to discern which, if any, of the high temperature determinations were the more reliable, suggested we needed more measurements and the combustion conditions. And actually more recently, very recently, so this year, Steve Klippenstein et al. have carried out a very high-level theory calculation for this reaction, and I've actually found another channel which might explain the strange temperature dependence of the system. So in this case, going back to what I was mentioning yesterday, they've done a couple cluster calculation using single double excitations and then using correction methods for the triples. They've then coupled that with variable reaction coordinate transition state calculations. So this is a relatively high level of theory based on this particular potential energy diagram. And the total rate here from the theory calculations is the black line here. It's reasonably consistent with most of the data, but some of this high temperature data is quite a long way from the theoretical calculations. And so the theoretical calculations seem to show that, this strange temperature dependence. It's possible that not all of the high temperature data is of high fidelity. So sometimes we get these inconsistencies. So, that feeds into the uncertainties of our overall reaction, and maybe some judgments have to be made about which data is the most reliable. But the most important thing about that theoretical work was actually a new channel suggested for this reaction HO2 plus HO2. So I said earlier, in standard models, this is forming H2O2. And really then, we're looking at high temperatures and pressures of that H2O2 decomposing to give us two OHs. But what the theory calculations suggest is that there is actually a direct route from HO2 plus HO2 to two OHs. And actually, the multiscale informatics type approach was also applied here to try and consolidate these discrepancies between experimental data. And there's also fairly recent data from shock tube study of Hong et al. And the multiscale informatics approach resolves the theory and experimental data and supports the presence of this new channel. And what they've then done is shown how important that might be for flame speed calculations at high temperatures over a range of different equivalence ratios. So particularly in lean conditions, there is a difference between the original hydrogen-oxygen model and the suggestions which include this new channel for HO2 plus HO2. Okay, so probably at stoichiometric conditions and rich conditions, this doesn't have a high importance, but when we come down to very lean conditions, then it does have an influence on the flame speed predictions. And that might be important if we want to burn hydrogen under lean conditions, for example, to avoid NOx in future hydrogen applications. And so I guess I asked at the beginning of the question, do we know the hydrogen system 100%? Well, no, there's still papers from 2022 which are suggesting improvements for the hydrogen-oxygen system. And actually, probably also quite interestingly, this new channel has an influence on predicting ignition delays for N-heptane air. So that might be surprising that quite a substantial difference. This is on the log scale here. Actually, slightly lowering the ignition delay times for N-heptane. So these hydrogen-oxygen reactions are, of course, the core of all combustion mechanisms. Every mechanism in combustion will include all these reactions. And they quite often have high sensitivities. Okay. So the second section for today's session is theoretical basis for chemical kinetics. And probably the first question to ask is, why bother with theory? It is quite hard work. Maybe not as hard work as setting up a new experimental facility, but it is quite hard work. And we do have uncertainties, as I tried to suggest yesterday, coming from our electronic structure calculations that are going to feed into any theoretical predictions of our rate constants. But the advantage of including theory in our approach is that actually they can help us to extrapolate, to give us rate constants at pressures and temperatures where we're not able to do experiments or we don't have experimental data. So if you remember, I was talking about the lift type experiments in the first session and saying, well, actually, we're normally conducting those at low temperatures and low pressures, so quite well away from the conditions where we might want to model combustion to be honest. But actually, if we combine those experiments with theory, so for example, if we have theoretical calculation of rate constants that we can apply over any temperature and pressure, but maybe use the experiments to constrain the inputs to that theoretical model, then we can use the models to extrapolate. And so, again, that supports the idea that for many systems, it's very useful to combine information that we have from experiments with theory and modeling to help optimize our system and reduce the uncertainties as far as possible. Some of these quotes I think I probably have taken from Steve Klippenstein, who, of course, is an evangelical modeler. So basically, I guess the view of the theory people is that actually, if we can get very high quality theory calculations for our systems, then that gives us a single source of data that will be consistent across mechanisms. So the idea that there are many different mechanisms out there, right? Somebody asked me this over lunch. For the hydrogen-oxygen system, I don't know, it was 20, 30 different mechanisms. But we should all be converging to the same thing eventually, shouldn't we, right? That we're trying to get as close to that high fidelity model that we know we can't get exactly there, but we're trying to get as close as possible to that. And at least for hydrogen-oxygen, we should be able to get close, not for more complex fuels maybe, but hydrogen-oxygen. So, theory might help us get there. Well, this might be something that Steve would say, at least for small molecules, theory can achieve comparable level of accuracy to experiments. Getting there, I would say. Getting there, yeah. I mean, for small molecules, anything in the hydrogen-oxygen system is a reasonably small molecule, but we do need to move beyond that if we want to look at other combustion systems, obviously. And I think, the fact that we can automate theoretical methods is also potentially quite useful. I mean, there has been some work on trying to automate laboratory experiments. That's perhaps a little bit more difficult. The theoretical people are now trying to work up towards automating these techniques so that we can get through large numbers of rate constant calculations fairly quickly. I guess my caveat with that would be, if we're going to do that, then I would also like to know what the suggested uncertainty in the rate constants are across a range of temperatures and pressures, so that we know what the quality is of the data that we're using. I mean, models do help us to support fundamental understanding of kinetics, there's no doubt about that. So the system that we just looked at there, the experimental data maybe looked inconsistent, but actually, high-level theory showing us a new channel for the reaction that brings everything together, that's pretty useful. So I've put a quote from Steve here. Future progress in the fidelity of the chemical modeling of combustion will benefit from a more widespread applications of theoretical chemical kinetics. So you would say that as a theorist, but also from increasingly intimate couplings of theory, experiment, and modeling. And so that's, I guess, probably the main theme of my lectures this week is, how we bring all of these different approaches together. So today I'm just going to talk about kinetics experiments. I can't remember if it's tomorrow or the day after, but eventually I'm going to talk about how we optimize systems as a whole, maybe using everything. So maybe using bulk data from rapid compression machines and flow reactors, etc., with models and also with theory calculations. So we bring all the data together within an optimization framework to try and improve the fidelity of our predictions. So I would recommend this paper by Jim Miller, Combustion Chemistry in the 21st Century. So developing theory-informed chemical kinetics models, and that will give you, I guess, kind of a history and also recent developments and where the field is heading. I think I've probably put too much in today, so if I end up rushing through a few slides, that'll be why. So the theory of chemical kinetics, we're ideally trying to predict rates at which reactants with a given energy distribution pass over to products. Okay, so this kind of idea, well, at least for some systems of the transition state that we looked at yesterday. So unfortunately for those of us who find it difficult, we do need a highly accurate description of the potential energy surface to be able to calculate rate constants. And we need to know the energy distributions of reactants and products. And even with developments of CPU resource, as I was talking about yesterday, it's difficult to go to very high levels of theory for anything but the small molecules. So once we've got our potential energy surface, then we then need to go on to predict reaction rate coefficients, so the rate at which we're forming products. And we can make simplifications. So collision theory is the extreme version, I guess, of a simplification. Transitions theory, the next stage up, and then master equation modeling, where we've got a full treatment of energy resolved kinetics is the final example. So why really even mention collision theory? Oh, by the way, I've written it in capitals here. There is a typo in the notes here, where I think in your notes it will say squared on this equation, then it should say 1/2. So if you've got your notes out, can you correct that, please? I guess the online version would get a chance to be correct. Collision theory is the most basic theory. I mean, the reference I've used goes back to 1969, in fact. So basically just to saying that the rate of reaction relates to the collision frequency for collisions with kinetic energy greater than this critical value, which we can think of as an activation energy, along the right orientation. So this is kind of repeating what I said yesterday. So the gas collision rate is given by this equation here, where we've got the number of molecules of A and B. We've got basically the collision distance, the reduced mass, and then this term expressing the influence of an activation energy. So this is fairly a simple approach. We can improve it slightly by using Leonard-Jones potentials to look at long-range interactions and to improve on the hard sphere assumption. And so I guess we don't really use this to model rate constants, but actually just in the last week or two, we've come up with a use for this, which is actually available in RMG, and I'll talk about this maybe a case study a bit later in the week. But actually, even though we wouldn't use this to calculate high accuracy rate constants, it's a common sense check for mechanisms, and particularly for reactions where we've got a new fuel, for example, or a new mechanism where there's a lot of estimation going on, where there's no detailed experimental or theoretical data for the reactions, and they've basically been estimated through analogy for similar species with similar functional groups. That happens a lot, and it's not wrong because we have to start somewhere with a new molecule or new fuels that we might want to look at. But actually, Hai Wang published a paper where they, I think, randomly went through a series of about 20 mechanisms to make sure that the rate constants over a broad range of temperatures and pressures didn't really exceed the limits which you would expect from applying collision theory. And they found some quite gross violations of this in a lot of mechanisms, and sometimes by, well, just for an example, I mean, the example that we found by using RMG to do this for us was, I don't know, more than 20 orders of magnitude out. So it exceeded the limits imposed by collision theory by more than 20 orders of magnitude. So common sense check on the mechanisms we're using, particularly where we have a lot of estimated rates. This theory is still useful. So going back to transition state theory, this focuses on the configuration of the reactants at the highest point on our potential energy surface, so the transition state, or where we've got this activated complex, as I think I said yesterday. And so transition state theory is studying activated complexes near this saddle point of the potential energy surface. And as I mentioned yesterday, generally we assume quasi-equilibrium between the reactants and the activated complexes, and then we're looking at the fluxes from the activated complex to the products to estimate our rate constants. So our initial state or initial reactants are here, the final state here, and then we are looking to predict the rate at which we're transitioning from a well which represents our initial reactants to one which represents our final products. And usually the transition state would look like a saddle in the potential energy surface, something like this. Okay, so according to transition state theory, then the rate constant is a function of the probability of being at the transition state, so this activated complex, and then the flux out of the transition state into the final products. So we can have both classical and statistical versions of transition state theory. We can formulate both. Statistical thermodynamic formulation allows a calculation of an equilibrium constant between reactants and complex from partition functions. So, but of course, we need to do that. We need accurate knowledge of the partition functions, and to know that, then we need accurate methods for calculating the potential energy surface. If we're using collision theory, then we only really need to know the height of the energy barrier. But if we're doing transition state theory calculations, then we need to know the shape of the potential energy surface around that saddle point, to include other internal degrees of freedom, for example. So this is a schematic, I guess, of a reaction between reactants A plus BC. We're forming the activated complex at the transition state, and then we've got a flux going over to products A, B plus C. We're going to have contributions from all the internal degrees of freedom, including translation, rotation, and oscillations, for example. And in transition state theory, we are constraining in the direction of the reaction path, so going over that saddle. Does anyone know what the symbol's called? I'm calling it a double dagger, but I'm not sure if that's right. Right, okay. So the double dagger sign indicates that one of the vibrational modes along the reaction coordinate is being constrained, and so it's removed from the partition function for the transition state. So that constraining is along the reaction coordinate through that saddle. Okay, so the rate constant then is a function of the probability of being at the transition state, which is related to the partition function of the activated complex and the partition functions of the reactants. Then we've got an expression which involves the activation energy, and then we've got the flux from the activated complex to products. And in this equation, we've also got a correction factor. The most likely things that we'll be including in that correction factor might be, for example, the incorporation of tunneling through the barrier, symmetry factors, etc. So that's the sort of basic form of the transition state equation. I think I'm just going to skip through this. So basically the summary is that we have to include all molecular degrees of freedom, which would include translation, rotation, and vibrational degrees of freedom. I think we don't need the detail there. Okay, so just to remind you, from yesterday, depending on the level of theory, that will give us different accuracies in terms of the location of the transition state, but it will also give us a different capability to represent the different internal degrees of freedom. So obviously, in terms of the basis set, the more complicated the basis set, the high level of detail in the basis set we can include. Then we can include different levels of excitations, and we've got different levels of detail in terms of representing electron correlation, going all the way from sort of none in the basic Hartree Fock all the way up to full configuration interaction. And so all of this is feeding into the accuracy of the potential energy surface that we're going to provide to our method for calculating the rate constant. So that's basically a summary from yesterday. So we're going to use then our choice of method for calculating the potential energy surface. So I guess really in that case we're just going to basically pick the one that we can computationally afford, that's most appropriate for our system, so go to as high a level of theory as we can. We've got the energy of the transition state relative to the reactants along the structure of the transition state. So we've got, for example, our barrier heights or our well depths. From the Taylor expansion of the potential energy surface, we've also got the vibrational frequencies, and then we can use that to calculate KT from transition state theory. The simplest level is representing vibrations using a harmonic oscillator type approximations. For some molecules, that will lead to errors, and we need to go to high levels of theory, including things like hindered rotors, more complex calculations, and to do that, we need better basis sets, obviously. Also, I should mention basically that occasionally we need corrections through to account for motion through the barrier called quantum mechanical tunneling, and that would be an additional correction to the method. So just to give you an example of how, I mean, we're going to look at this in more detail probably in the last session today, but of how uncertainties can propagate here. I mean, maybe this is a fairly pessimistic example. So what this is showing is if from our electronic structure calculations, we've got an uncertainty in our barrier heights of 1 kilocal per mole, it's about equivalent to 4 kilojoules per mole, then what level of uncertainty will that feed into in our transition state theory calculations for the rate constant? Well, actually, it's temperature dependent. So at high temperatures above 1,000 Kelvin, actually, even 1 cal per mole error leads to fairly low uncertainties in the rate constant. But as we go to lower temperatures, the uncertainty in the predicted rate constant will increase. I think nowadays, unless we had larger molecules, we'd be aiming to get to probably half a kcal per mole, or maybe even less. I mean, 1 kilojoule per mole, I guess, would be an aim, and that might lead to errors of about a factor of 2 at low temperatures. Okay, so this, I suppose, is addressing the question, can theory do as well as experiment? For small molecules, yes, we do much better than this, but for large molecules, it's a little bit more tricky. Okay, so deficiencies in the simple transition state model would be this assumption that we're using harmonic oscillators and the fact that we're using simple representations of a tunneling model. So in order to include things like anharmonicities, hindered rotors, multidimensional tunneling, then we would need a higher level of theory in terms of our ab initio calculations of the potential energy surface. So for larger molecules, I guess we're in a more tricky position because we might be looking at, errors of this type, and we'll look at a couple of examples later, but which are going to propagate through to our rate constant calculations. So what does that mean? Well, quite often what is done, either in a statistical framework or I suppose in a, I want to say ad hoc, informal framework, is for systems where we've also got some experimental data, we can couple the two things together. So we can use the experimental data. I've put the word tune here, but I would rather use the word optimize in a statistical framework, I suppose. But we can use the experimental data to help tune our barrier heights to get closer than within 1 kcal per mole. And if we do that, then perhaps we've got tighter constraint on the main inputs to our reaction rate modelling that will allow us a better fidelity model that we can then use to extrapolate to temperatures and pressures outside of the experimental regime. So that will make more sense when we look at a couple of examples from Shannon and from Burke a bit later on. But historically, that has been going on in a kind of non-formal framework for quite a number of years, that people use a lower level of theory to calculate the potential energy surface because they can't afford to use higher levels of theory, but they have experimental data related to the rate constant over limited temperatures and pressures, but that can give information that helps us to tune the barrier heights to improve the modelling of the rate constant using theory. So I'm working up, I guess, to hopefully end this session with a few words about master equation modelling. So master equation modelling is using energy-specific rate constants within a framework where it represents basically both energy exchange and also chemical reactions at an energy-specific level. So to do that, we need microcanonical rate constants. So we need rate constants that are not rate constants that apply as an average over the Boltzmann distribution, but are specific to a given energy level for our system. And so these are going to feed into our master equation modelling a bit later on. And if we integrate these over the Boltzmann distribution, then that should give the same as the transition state result for the rate constant. Okay, so in this equation here, our microcanonical rate is given by, or is a function of, the sum of states in the transition state from energy 0 to n, from E to n plus NE, and then NE is the density of states at the energy E for the reactant S. So in the master equation model, we're going to specify energy grains all the way from the ground state up to excited levels, and we're going to need microcanonical rates for each of those energy grains in order to be able to predict the overall rate constant. I don't know an awful lot about, or I don't know very much at all about variational transition state theory, to be honest, but I thought I'd mention it because actually it's a method that crops up in the calculation of rate constants, particularly for reactions that either have a small or no energy barrier, so where there's no obvious transition state. This is important for radical reactions, for example. So in transition state theory, the location of the dividing surface is variationally optimized either to maximize the Gibbs free energy of activation in a canonical ensemble or to minimize the number of states of a generalized transition state in a microcanonical ensemble. So here what we're doing then is we're optimizing the transition state for each of the internal energies. So this is a much more expensive method than standard transition state theory. And we might also even include each quantum number for example, for molecular rotations. So basically what we're doing here is re-optimizing the position of the transition state for different energies and for different internal energies. So you will see basically this mentioned for some of the reactions, the radical reactions that we might talk about later on. So transition state theory is valid in gas phase bimolecular reactions where we've got efficient enough collisions to repopulate the excited state. So we're basically maintaining that equilibrium between the excited state molecule at the transition state and the reactants. for unimolecular reactions, this isn't going to happen unless the pressure is extremely high, okay, because the excited states are not going to be in local equilibrium. So we've seen that basically in those cases, the rate constants fall off as pressure is lowered. So in that case, the reactive states are going to be depleted faster than they can be repopulated. So transition state theory is not the right method of choice for pressure-dependent reactions. Some of this might repeat what I said yesterday, but basically, if we go through the theory for pressure-dependent reactions, the starting point would be Lindemann theory for unimolecular reactions. So here we've got the activation of our reactant A through collisions with our third body M, and that reaction is reversible and second order. And then we've got the second step where we've got the reaction of our activated molecule to products, and this is first order. And so we've got in the first reaction, second order reaction K1 and the reverse K minus 1, and then a first order reaction here in the second step. So A is our reactant molecule, which can reach the excited state on collision with this third body, and we've said that basically many reactants can act as third bodies. Then it can either be collisionally deactivated to go back to the reactant, or it can form products. So if we have got this quasi-steady state between the reactants and the excited state, then we can apply the quasi-steady state approximation to the activated complex A star, and that will give us K uni, which is a function of a pressure expressed through M. So at high pressures, this second order reverse rate constant is going to be much higher than K2, which is forming our products. And so if we simplify this rate constant by assuming K minus 1M is much larger than K2, then the ends will actually cancel, and we can see that we've got a pressure-independent reaction there. The overall kinetics actually then at very high pressures will be first order. At low pressures, we have the opposite situation. So in this case, K minus 1M is going to be much smaller than K2. So then the K2s will cancel, and we have a bimolecular step, which is rate determining. Okay, so this is why we have different orders of reaction at high and low pressures. Okay, I think that is sort of a repetition of what I said yesterday. The problem here is that we've got no account of the energy dependence of the activation, and we're completely neglecting internal degrees of freedom of our molecule. And so this theory is going to underestimate the rate of activation. So if we look at real systems and we plot 1 over K uni versus 1 over M, this is not generally linear. We're also neglecting the fact that the unimolecular step specifically involves particularly one form of molecular motion. So the orientation of the system, for example. So that was extended, the Lindemann theory was extended by Hinshelwood by basically trying to model internal modes for A using simple harmonic oscillator approaches and using statistical methods to determine the probability of the molecule being collisionally activated to this reactive state. Okay, so I don't know if I really want to go through the details here. But basically, now we've got what did I want to say about this? What I wanted to say was on the next slide, probably. We've got basically a rate constant now, which I don't know what I want to say. I'll move to the next slide and see what's on there. Yeah, okay. So basically now then, we're summing over all the levels of energy which are greater than a critical energy E0, which is our activation energy. And the vibrational quantum number of state with energy EM is M, and that gives us an equation here. So if we integrate over all the energy levels, then we get a rate constant which now involves the frequency of harmonic oscillators, so the number of harmonic oscillators, S. And so the more oscillators we have, then the greater this correction will be. So the greater the correction will be for larger molecules, for example, which have a greater number of oscillators. And then we move on to RRK theory. And in this extension, we're now looking at energy being localized in specific modes of molecular motion for that unimolecular step to take place. So now we're looking at the orientation of the molecules as well. So the molecules have many internal degrees of freedom, and the reaction will only occur when we've got some specific degree of freedom which acquires the critical amount of energy. So here then, we're not just looking at this excited molecule, but we've got a specifically excited molecule called the activated complex. So we've got a new reaction step now where we're going from the generally excited molecule to one which has specific orientation to give us a reaction over to products. So this is of the order of vibrational frequency, and K2A is generally much smaller. So that what that means is that conversion of our generally excited molecule to our specifically excited activated complex is going to be the rate determining step here for the conversion of A star to products. So in this reaction, the rate K2A, so the conversion from the generally excited molecule to the activated complex, is much less, much smaller than the rate constant going to products. And so the slower of those reaction steps will be the rate determining step. So RR, let's see. So if we're not trying to move this now to energy-specific formulations, then the probability of locating a minimum amount of energy out of the total amount of energy in a dissociation mode is given here. And then if energy randomization takes place rapidly, then we've got this statistically distributed vibrational energy, which is related to this probability, and we can calculate the rate constant for a specific energy according to this equation here. So K2 is going to increase with energy as we move up and down the energy ladder, since the probability of locating a local amount of energy in one particular mode is going to increase as the overall energy increases. And it's going to decrease as the number of oscillator increases, because of the more oscillators we have, then the more modes there are to spread the energy across. So K2 is likely to become smaller as the molecule becomes more complex. So the final extension to this is RRKM theory, and this is basically a sort of microcanonical formulation of the transition state theory. So it's what we need really to calculate the microcanonical rate constants that we're going to then use in the master equation approach. So it's basically applicable for transition state dividing surfaces where we've got a well-defined energetic barrier. And if we haven't got a well-defined energetic barrier, then we need to use something like variational transition state theory. Again, I don't know if I want to go through all this detail, but I think the basic thing to take from this is that now everything is related to an energy level. So the reaction mechanism can be rewritten now to take account of the fact that the rates of collisional activation are energy dependent. So instead of having an average over the Boltzmann distribution, we've got specific energy level values for our rate constants. And so for a reaction here where we're moving through collisions to an activated complex and then to form products, we've still got this quasi-equilibrium between the activated complex and the reactants, so we can still use the quasi-steady state approximation here to give our rate expression for the formation of products. But now here everything is energy dependent. So from this we can identify the unimolecular rate coefficient for a specific energy range in this way. So it depends on energy-specific rate constants and also the pressure. So if we want to get back to the thermal rate coefficient, then what we have to do then is integrate from energy 0 up to infinity for this expression. What do I want to take from this? So what I want to take from this, I think, is that the rate constant K2 is derived from applying the QSSA approximation, so the steady state approximation to the activated complex, the same as in our KK theory, but now we're basically just breaking down the overall reaction into energy contributions from different motions like translation and from rotation and vibration. So to do that, we need to know the partition functions for these different modes. So if we go to high pressures where we've got very effective collisions, then our RKM theory should collapse to be the same as the transition state theory model, and the two theories should coincide. But the transition state theory isn't capable of giving us the kind of fall-off behavior that we can get from RKM. So those techniques, transition state theory and RRK and RKM theory, are used where we've got a well-defined energy barrier, and where we haven't, where we've got a shallow barrier or no barrier, then we have to use the variational approach that I mentioned earlier. Or we have to use alternative empirical-based approaches, such as an approach using inverse Laplace transformations. And these approaches are kind of all embedded in the master equation models. So to give a takeaway method, the most commonly used theoretical methods are accurate within two limits. When we've got the fast relaxation with respect to the timescales, then we can use transition state theory. So here basically we've got fast collapsing to a thermalized system where we've got the Boltzmann distribution, and we've got energy transfer happening on much more rapid timescales than the kinetics. If we've got slow relaxation, then we need an energy resolved description like the RRKM theory. That's going to be more appropriate. The more general approach is to use master equation modeling, which can deal with both of these limits and everything in between. So master equations will facilitate kinetic simulations over multi-well potential energy surfaces where we might have energy transfer processes and kinetic processes happening on more similar timescales. Okay, so master equation models can be used in these circumstances where the timescales for thermalization are competitive with the kinetic timescales. And the example I mentioned yesterday of non-Boltzmann kinetics was an example like this. So I'm not quite sure what time I'm supposed to break. Anyone know? Got 5 minutes. You want to carry on? Yeah, I'll make a start, and we can always come back to this. So the master equation approach, as I say, is an energy-resolved approach. It's called energy-grained usually because we tend to, because we've got such a high number of energy levels, we tend to package these into what's called energy grains. And so it involves basically the calculation of energy resolve rate coefficients using microcanonical transition state theory. And that will be coupled with collisional energy transfer models. So as a input to the approach, we need information on the microcanonical rate constants at different energy levels. We also need a model of collisional energy transfer, and we combine those together to construct a model that can describe phenomenological rate constants that might arise from the competition between these two things. So typically, we would apply a one-dimensional master equation where where we're basically looking at energy resolved systems, but we are averaging the angular momentum. So Mesmer works like this. There will be examples of two-dimensional master equation simulations where angular momentum is also a variable. So in Mesmer, this is the Leeds base code, by the way, this assumption is made because from experience, for most systems, errors that we've got feeding into the master equation from energy levels from our potential energy surface or from errors in vibrational frequencies, etc., tend to have more impact on the predicted rate constants than the errors induced by averaging over the angular momentum. So it's a simplification, I guess, worth making for saving computational cost. Okay, so this is a typical example, not very different from things that we've looked at already. A plus B, forming an activated complex, and then moving potentially over transition state barriers to finally form products. So master equation models can deal with these multi-well systems, not just a single transition state. So that's one of the advantages of them. In this case, then, the reactant, all of these are moving up and down the energy levels depending on how much energy is supplied to the system. And the reaction must be activated and enough energy supplied to overcome the barriers to form the products. So we've basically got energy transfer going on through collisions with the bath gas. Some of these collisions will be activating to form our activated complex, and some of them deactivating. We treat these energy transfer processes as random processes, and therefore we can treat them using stochastic process theory. So also on this diagram, you'll see that we have energy-specific rate constants representing the fluxes from the activated complex into the products. So we've got this competition between collisional energy transfer and the flux from the transition state, which is the chemical reaction part of the system. Okay, so what we're trying to get out of this is a phenomenological rate constant prediction for different temperatures and pressures. But we're doing this at an energy resolve level, and so we're doing this at the microcanonical level in order to be able to predict at the macro level. And so we need as an input to this microcanonical rate constants, and we try to simplify the computational aspects of this by bundling together row vibrational states that have similar energies into these energy grains and describing the time evolution of transfer between these energy grains. So the energy grains, obviously the more energy grains we have, the more resolved the method will be. They tend not to span more than a few kilojoules per mole, which I guess is of the order of the level of uncertainty that we should have in our inputs to the system. Okay, so I wonder if I should leave this till after the break. Should I leave this till after the break? Yeah, okay. I'll leave that till after the break. So here, guys, is the equation for the energy grain master equation model. Here then what we're doing is the model equation is representing the rate of change of population density within our specific energy grain. And then we've got terms representing the various different processes. So the first term here is representing the collisional energy transfer from other energy grains, in particular isomer that we're looking at. So this is movement of energy up and down the energy ladder for that isomer. And omega here is the Lennard-Jones collision frequency. And here we have the probability that the collision with the bath gas will result in a transition from a grain with a certain energy to a grain with energy E. Okay, then we've got the population loss from collisional energy transfer from our energy grain E into other grains. And then we've got a reversible population loss or gain through reactions that transfer population from one isomer to another isomer. So this is expressed as a function of the probability within the energy grain multiplied by, so this is kind of like a concentration really, multiplied by the microcanonical rate constant. So we've got two terms here which are the opposite sign of each other. And then we've got the reaction going to products, again the microcanonical version of that reaction. And then we've got population gain and loss via association, dissociation reactions. So that, of course, will be a system of equations for each of the energy grains in our model. So the more tight well, the higher the resolution, I suppose, of the energy grains, and the more equations we've got to solve in the system. And then we need mass balance closure. So we've got another equation. This is not energy specific now for our products. And here, what we're doing is integrating over the energy grains from E0 to infinity. So basically, this is the reaction rate term here. It's basically just the forward and reverse reactions summed over all the energy grains. Okay, then we're solving the system at least. Okay, so this is basically a description of the Mesmer code, which is the Leeds-based code. And actually, the Argon code also uses this matrix diagonalization type methodology. It's not true of all the master equation models. But here, we use matrix diagonalization techniques to turn this into a discrete form because the whole system is actually fairly sparse, and so we can use diagonalization to give us a discrete form where M is transition matrix, and that determines the population evolution. due to the collisional transfer processes. So the number of eigenvalues in the system is going to be equal to the number of energy grains. And the grain size is a balance between how much microscopic detail we want and how much we can expend in terms of computational expense. So in general, we're looking for the smallest eigenvalue of the system. So we'll have lots of different eigenvalues which are representing different timescales in the system. In general, not always, but the energy transfer processes will equilibrate relatively quickly. And so they will be large negative eigenvalues. And it's the slowest eigenvalue, so the smallest eigenvalue, the smallest negative eigenvalue, which is representing the overall chemical process. And so that usually corresponds to the rate coefficient. So what do we require as inputs to the master equation model? So we require microcanonical rate constants, and we need barrier heights, we need vibrational frequencies, and we need a representation of the energy transfer model. So obviously, to get the barrier heights and well depth frequencies, we've got to use electronic structure calculations to get our potential energy surface. And so the level of theory that we use to calculate our barrier heights and frequencies, etc., the level of accuracy from the theory is going to feed into any uncertainties in the predictions of our master equation model. And so a bit later on, I'll show you, how that feeds in and the effect of different levels of theory on the prediction of our rate constants. We also need collision frequencies, and in terms of the energy transfer model, the usual approach is to use what's called the exponential down model, and then calculate the upward transitions just using a detailed balance for that. So we will have extra parameterizations for that exponential down model. I think, to be honest, this is probably similar to something I showed yesterday. So our rate constants for collisions, this is the hard sphere formulation, which I think I did show earlier. And then we might have a correction for van der Waals forces, for example, through the Lennard-Jones potential. So we're going to have some additional parameters related to Lennard-Jones formulations here that are going into our master equation model. Okay, so this is basically just a schematic diagram, really, of what the system might look like. This is for an isomerization and dissociation system. So we're going to get our microcanonical rate constants from our RKM theory. We need these well depths and barrier heights for our transition states. And then we will solve the energy master equation, and the chemically significant eigenvalues will give us information on the phenomenological rate constants for the different reactions here over, we can run the model over a range of different temperatures and pressures, basically. So this issue about chemically significant eigenvalues, ideally, if our system is nicely behaved, then all of the eigenvalues of M will be negative, and we will see some kind of separation in the eigenvalue spectrum. So the majority are going to be large and negative, and these are governing the time evolution of the energy transfer processes. So these should be processes that are rapidly equilibrating, which is related to that large negative eigenvalue. And then we will have a smaller group of eigenvalues called the chemically significant eigenvalues that are less negative. And it's actually the smallest eigenvalues which are actually determining the chemical behavior of the system. So these are governing the chemical evolution of the system. So the number of chemically significant eigenvalues should correspond to the number of distinct chemical species being modelled. And it's usually the sum of a number of Wells and source terms in the model. So if you remember from yesterday, our species are defined as being sort of sitting down in these wells, And obviously, we've got source terms from the reactants in the model as well. So if we get this nice separation of timescales, then we can basically set up our matrix equation and basically just look at the smallest negative eigenvalues, which are related to these chemically significant eigenvalues, to determine our rate constant for the chemical system. So this is fairly straightforward if we get this nice separation. But for some systems, we don't get this nice separation between the energy transfer processes and the chemical processes, and the eigenvalues can start to cross. And then it gets more difficult because we can't easily define chemical rate constants. And so I think there is an ongoing debate about how to handle systems like that. I mean, the master equation system can solve those, but what I want as a modeler is a nice representation that you can feed into our modeling systems. So we're used to Arrhenius expressions, or we're used to fall-off expressions or whatever for our models. And where we see this interaction between energy transfer processes and chemistry, it does become more difficult to define specific species. So there are a number of open source codes for doing master equation modeling. The Leeds code I'll mention first because I'm from Leeds. It's called MESMA. You can get it from SourceForge. It has got quite a comprehensive manual. And it can be used for multi-well systems for the types of processes that we want to look at. It provides you, so it doesn't do electronic structure calculations, so you have to feed in the output from your electronic structure calculations to set up your potential energy surface for use in the master equation model. And it will output for you chemically significant eigenvalues. It will fit phenomenological rate constants for you. It will give you model species concentrations over time or selected outputs. The other thing which MESMA does, I'm not sure if the other codes do this or not, but basically it allows you to incorporate experimental data into the master equation modeling. So you might have a system with large molecules, a large number of atoms, and you've only got a low level of theory describing your potential energy surface. So you might be worried about the accuracy, for example, of your barrier heights or your well depths or your vibrational frequencies. But you might have some experimental data over a limited set of temperatures and pressures, for example, that give you more information on your system. And MESMA will allow you to use that experimental data to give you an optimization of other inputs to the code. So, for example, a transition barrier height, transition state barrier height. It will allow you to fit that using an optimization method. And that means that you can therefore combine experimental data with your theory calculations to give you a better constraint on the overall system. So I'll show an example of that in a minute. MESS is the other matrix-based method which has been developed at Argonne National Labs. I think it is now open source. I don't know, hands up for anyone using it? No. I spoke to one person who's using it, I think, over the break. And multi-well is a slightly different approach. It uses a stochastic approach rather than the matrix methodology used in the other two that comes from John Barker's group. So these codes are openly available for you to use, just with caveats really about, they're not really black boxes, I suppose, is the point. You have to know something about what you're doing and the inputs that you're using. Okay, so I'm going to skip that, so not really necessarily related. So going back now to this kind of theme of understanding uncertainties. So now we're kind of layering up potential uncertainties through our modeling system. So this is basically the graph that I've kept showing in terms of electronic structure calculations, in terms of the level of theory that we're using and how that might influence the accuracy of our outputs, which would be transition states, well depths, frequencies, etc. Then we're feeding them into our modelling of our rate constants. And again, we've got a similar diagram. So it's a matrix diagram where we've got increasing levels of detail in our theory. So in terms of the description of the microscopic rate constants, so the energy-specific rate constants, we're going from simple levels of theory like RRK all the way through to RRKM, and maybe using variational methods like variational transition state theory at the higher levels of theory. And then we've got levels of complexity in terms of the collision dynamics model. So the simplest would be the Lindemann-Hinshelwood approach, going to the one-dimensional master equation, which is energy resolved, and the two-dimensional master equation, which is energy and angular momentum resolved. And so I guess, you know, the highest level of theory would be extrapolations to complete basis set and full configuration interaction for your electronic structure, and coupled with, well, either RKM, if we've got well-defined barriers and a two-dimensional master equation model. So it's fairly clear that any uncertainties that we've got coming from our electronic structure calculations are going to feed into our master equation model and therefore potentially feed through to uncertainties in our rate constants. So I just want to I mean, there hasn't been a huge number of studies that have looked at this, but there have been a few. So I just want to show some examples here. So what, you know, we've got quite a large number of parameters that we have to feed into our master equation model. Barrier heights, well depths, vibrational frequencies, collision frequencies, and energy transfer parameters that go into our exponential down model. And these, the accuracy of these are going to depend on the level of theory that we're using. So there are some emerging studies, I would say, that have basically propagated these to give us an understanding of which of these parameters are going to have the largest effect on our predictive rate constants. So, you know, this could be tens of parameters going into our model, or maybe, you know, even hundreds. But like with most systems, there's not going to be a huge sensitivity to all of them. And I guess it's useful to know which of these types of parameters are going to have the biggest effect on the predictive rate constant. So if I just asked you intuitively, what would you say is the most likely sensitive parameters? Shout. Barrier heights. Anyone want to offer another suggestion? We'll see. Okay, so this was an example for N-propyl plus O2 system. So in the entry here, we've got the alkyl radical coming from, so N-propyl is the alkyl radical coming from propene plus oxygen. And it's typical kind of low temperature pathway for an alkane. So addition of oxygen forming the peroxy radical. So this is a species here, relatively stable radical down in a well here. And then potentially isomerization to QOH. And we've got two different possibilities there. And then going from QOH to products. And so depending on the pathway chosen, we're either going to form another OH, or we're going to form an OH, which would be increasing the reactivity relative to forming HO2 through this pathway, which would be lower reactivity pathway. And we've also got some direct routes going from RO2 to products as well. So it's quite a complicated multi-well potential energy surface with several transition states and wells corresponding to the RO2 peroxy radical and the two QOH species. So as inputs to the model, we've got obviously the well depths for each of these species. We've got barrier heights for each of these transition states. We've got vibrational frequencies. And we've got parameters that are part of our exponential down model. And so we're going to assume uncertainties in all of these parameters. I think 67 parameters were varied in total. And then we use a kind of quasi-random Monte Carlo approach to propagate these uncertainties. So in terms of the energy levels, we're assuming errors or uncertainties of plus or minus 0.5 kcal and 1 kcal for the stable species. So these will be the well depths and the transition states here. So a larger uncertainty for the transition states than the well depths, up to 1 kcal per mole. Frequencies, plus or minus 20% for hindered rotors, and the imaginary frequencies related to tunneling corrections, and 10% error for harmonic vibrations. And then we've also got a plus or minus 50% in the pre-exponential factor for the delta E down model, and 20% variation in the Leonard-Jones parameters. So, I mean, these are all estimates, to be fair. So even when you're propagating uncertainties, you know, there's an expert judgment goes into the level of variability that you're going to propagate. Okay, so this is the reaction system then. We've got 9 different reactions that we're predicting rate constants for using the master equation model. And as I say, we used a kind of pseudo Monte Carlo type approach. So, for those 67 parameters, what we're doing is sampling, using a quasi-random sample in this kind of 67-dimensional hyperspace, if that means anything to you. I'll say more about uncertainty methods on Friday. We might run, you know, 1,000 simulations or 2,000 simulations where we're drawing from those uncertainty distributions. And so what we get at the output of that then is probability distributions for our rate constants. And so on the right here, what we've got is the frequencies of the predicted normalized rate constants. So the tighter the distribution here, then the better constrained our prediction for the rate constant. The broader the distribution, the more uncertain our predictions become. Okay, so for reaction R1, which is the formation of RO2, we've got a fairly tight distribution there. So maybe up to a factor of 2 uncertainty in the predicted rate constant. For the other reactions, we're actually probably looking at uncertainties of between 4 and 6. So 3 sigma variances is probably a little bit pessimistic. We normally probably take 2 sigma as a typical measure of the error. But if we take 3 sigma variances, then we're getting most values are within 4 to 6 of the most frequently predicted value. So output uncertainties of between a factor of 4 and 6. Okay, so relatively large uncertainties in our predicted rate constants using the assumed uncertainties for the inputs. And then what we want to know, I suppose, is what are the causes of the variability in those predicted rate constants? So what are the main of the majority of the input parameters, the most important input parameters that are causing those distributions to be so wide? And we can analyze that using sensitivity analysis. Again, I'll say more about the methods on Friday, but just to show you some results. So the intuitive suggestion when I asked the question is that it would actually be the barrier heights, which were the most important contribution to the uncertainties, and that does turn out to be correct. Very good. So if we take a reaction 5, which is the isomerization of RO2 to one of the QOHs, then we can look at the sensitivity. So what this number means is that if a parameter has a sensitivity of 0.667, what that means is it's causing 66.7% of the variance in the predicted output. Okay, so that's 2/3 of the variability in the predicted output is coming from the uncertainty in the transition state for that reaction. That makes sense. So, I mean, basically, all of these sensitivity indices for a particular set of conditions will add, or should add up to 1. So you're trying to represent the whole of the variance in the output by assigning the causes of that variability to the different parameters. So I'm just showing the main ones here, but if you take the sum of the sensitivity coefficient for the transition state and for the well depth for the energy for RO2, then that comes to 85% of the output variance. It's the majority of the output variance. And so if we wanted to reduce the output variance in our prediction for this rate constant, then we should focus on improving our input information for these two energies. And actually, this was fairly consistent across different pressures. We went up to 1,000 atmospheres and different temperatures. And the same was true for reaction 6. So this is the direct reaction going from RO2 to HO2 plus propene. Again, the transition state for that reaction is about 2/3 of a contribution to the overall variance, slightly lower at higher temperatures. And the RO2 energy is the second most important. At higher temperatures here, we do see now a contribution from the pre-exponential factor for our delta E down model. So there's 8% contribution from this. Okay, so our intuitive kind of feeling is that, you know, it's the barrier heights and well depths that are going to be the most important, and this, I guess, shows that to be the case. We didn't see a huge influence from uncertainties in any of the frequencies, but we only varied, I think, by up to 20%. So it's possible, I suppose, that you know, could be based on our initial assumption. Okay, there was another study done in 2013 by Prager et al. For an isopropanol system. It's a slightly different approach that they took here. So what they did was applied various different levels of theory to calculate their potential energy surface. So they included density functional theory methods, perturbation methods, complete active space methods. The composite methods I talked about yesterday, like CBS-QB3, which is the cheaper of them. These were all calculated using Gaussian and MolPro, and then they looked across these different methods to see what the level of variability was in the predicted transition states and well depths, etc. And then they propagated that through to predictions in the rate constant. And what's quite interesting about these alcohol plus OH reactions is we actually need to know site-specific hydrogen abstraction rate coefficients for these fuels. I'll talk about that more later in the week. But actually, there are various different sites from which OH can pull a hydrogen to form water and the alkyl radical here. And it actually really matters which site is the most frequent, because that will affect whether the chemistry goes down chain branching route or goes down chain propagation or chain termination route. And actually, these site-specific abstractions are quite difficult to obtain experimentally. So experimentally, it's relatively easy to get the overall reaction rate with OH, but actually predictions of ignition delays are not particularly sensitive to the overall reaction rate. They're much more sensitive to the branching ratios of the different sites of abstraction. So theory can really help us here if it can give us you know, reaction rates for those different sites and give us the branching ratios. Okay, so what they did here was basically, first of all, was to apply the different theory methods to get the potential energy surface and then look to see what the variability in the energies was. So what they found was there was considerable scatter in the calculated barrier height, and this is ranging over more than a kilocal per mole, actually about 1.5 kcal per mole between the different methods. There was less variability in the calculated frequencies, but even these could vary up to nearly a factor of 2. So actually, I don't know whether that suggests that our assumptions of 20% in our study were perhaps a bit optimistic. And then, of course, these parameters feed into uncertainties in the predicted rate constants when you come to use master equation methods. They didn't actually look at uncertainties in the energy transfer in this particular study, but actually in the Propal system we didn't find those to be massively important anyway. What you can see in the grey here is the kind of a priori uncertainties based on these uncertainties in the calculated barrier heights. And you can see here that there's a temperature dependency on the level of uncertainty. So the system the predicted rate constants are less uncertain at the higher temperatures, but actually the uncertainty increases as we go to lower temperatures. And this is a log scale. So it's not that dissimilar to what was found in the Propal system in terms of, not quite an order of magnitude, but maybe a factor of 5 uncertainty there. And then what they did was they used some experimental data in a kind of Bayesian type approach to try and better constrain these barrier heights and to reduce that uncertainty. So what we've got here now is the constrained model using basically available experimental data. And what you can see here is that the posterior distributions are far more tightly constrained than when a priori theory was just used on its own. And so the experimental data here is reducing the uncertainties in those barrier heights, and that's feeding through to a better constraint on the predicted rate constants. And what the outcome of this is that actually if you produce the joint probability distribution of the inputs now, these constrained inputs, that there will be correlations between them, okay, because you've used an optimization approach. And so there are correlations now between some of the energy barriers and frequencies, for example, and this is with the imaginary frequency here. Okay, we have a better description of our potential energy surface, but now we need to pay attention to these correlated inputs. So what this shows is that by combining theory with experiment, we can do much better in predicting our rate constants. So the errors are overall much lower. So actually, because they applied various different levels of theory, you might, I guess, ask which theory was the best. And it's actually a little bit difficult to answer that question based on the study. The high level of theory was the CASP P2 method. There's 2 density functional methods there and a fairly low-cost composite method. All of these methods gave energies which were reasonably close to the posterior estimates of where the experimental data was used to constrain the system. But actually, out of these methods, they both gave slightly larger discrepancies with the posterior estimates for different frequencies in the model. Okay, so one of the density functional methods and the composite method gave 50% errors with respect to the posterior estimates for one of the real frequencies, and CASP P2 and the other density functional method gave errors with respect to the imaginary frequencies. So it's a little bit difficult to actually say which of the methods was overall the best theory method. But I suppose probably the useful thing about this is it shows that the transition state theory calculations were generally consistent with the experimental data within the suggested uncertainties. Okay, so the last thing I want to look at, I think, today is Another example where where basically experimental data and theory calculations were combined, and that's relatively easy to do in MESMA because it has this fitting facility. And so you can feed in prior estimates for your transition states or well depths, etc., frequencies, but you can allow them to float in this optimization procedure. So again, you do need an idea of what the level of uncertainty is in the values that you're feeding in, but then you can use available experimental data to better constrain those and therefore to reduce the overall uncertainty in your rate constant predictions. Okay, so this was a study that was done at Leeds for a system related to DME, or dimethyl ether oxidation. So this is a potential alternative biofuel that could be used in vehicles. And a fairly low level of theory, CBS-QB3, was used to estimate the inputs to the master equation, so barrier heights, etc. And actually, we're sort of, it was kind of a thought experiment, really, because if you know that you've got the capability to do experiments to better constrain these parameters, I guess you ask the question, well, what experiments should we do? What are the best experiments that we can use to give us a good optimization of the inputs to the system? And so this was a kind of case study in asking that question. This is the potential energy surface here. So this is the alkyl radical that comes when you abstract hydrogen from DME. And then you're going to form an RO2 through addition with oxygen. And then you're going to go to QOH. So again, typical low temperature reaction sequence by going over the first transition state. And then you're going to go to products by going over the second transition state. Okay, so we're calculating these well depths and barrier heights using a fairly low level of theory, so we know that there are going to be uncertainties there. And actually, rather than do the experiments first and then use that data, it's possible to sort of do the modeling first and then ask the question, what are the best experiments to use to constrain the system? And so to do that, what we're doing is we're allowing the input parameters to vary. So again, we're using a kind of Monte Carlo approach here. And then we're doing a sensitivity analysis approach to say, okay, if we simulate experimental data, which of those experiments is going to help us best constrain the inputs to our model? I'll try and explain that a little bit better from this diagram. So what we know is that if we're using, in general, we kind of stuck with low temperature, low pressure experiments. They're not really being carried out at the conditions where we want to model combustion. We want our rate parameters to be able to model over high pressures. These pressures are in kilopascal, so that's going up to 12 bar. And you know, from the low temperature regime up to reasonably high temperatures, 900, 1,000 Kelvin. And so actually what we did was to simulate the master equation code to predict rate constants with input variability in our parameters for the master equation, and to carry out a sensitivity analysis to say, okay, what are the most sensitive parameters that are affecting the prediction of our rate constants at conditions where we might want to model combustion. And probably not surprisingly, these are the energies of the two main transition states, TS1 and TS2. Okay? So that's what's going to affect most our prediction of rate constants. And we know that we have not constrained these particularly well because we used a low level of theory, a composite method. We can carry out experiments, and in the experiments we've got various outputs. OH yield, relative OH yield might come from LIF experiments, and they will also give us a rate coefficient for the alkyl loss, and also a time constant corresponding to the long time formation of OH. But we're limited in terms of the temperatures and pressures that we can use, and so the experiments, as you can see, are all at very low pressures. But the useful thing is, particularly for the OH yield, if we try to predict the OH yield, which is linked to our experimental conditions, then the sensitivity is to exactly the same two parameters, so to these two transition states. So what that tells us is if we can get high quality data on OH yields from our experiments, even at low temperatures, below 500 K, and very low pressures, it will constrain our two transition states. And if we constrain those two transition states, then we can reduce massively the uncertainties in our predicted rate constants at combustion conditions. That makes sense. So I think what I found interesting about this was actually, you know, we can carry out experiments at conditions that are miles away from where we're trying to model. You know, this is miles away from a gas turbine. But actually, if we couple it with theoretical calculations, we can get fairly well-constrained predicted rate constants from using those experiments. Okay, so this is what we did. So the experiments were carried out, and then we used an optimization, just using a market fit that's available in MESMA, to better constrain our transition states in the model. And actually, I'll hold my hand up and confess, actually, that basically our constrained values were outside of the range of uncertainties that we estimated as inputs. We couldn't actually model the experimental data with the input uncertainties that we first picked. We had to make the uncertainties wider. So the uncertainties from the CBS QB3 method were bigger than we thought, actually. But when we use the experimental data, now we're able to constrain the uncertainties for all the rate coefficients to within a factor of 2. Okay. So, you know, we might have started out with uncertainties of a factor of 10, for example. So that's a massive improvement by including the experiments. And as a result of the optimization process, we end up then with correlated inputs. So we end up with quite strong correlations between the well depth for RO2 and transition state 2. But actually, I don't know if this was surprising or not really, but not very much correlation between the two transition states that were constrained most by the experiments. Okay, so then for the constrained model, we did a final sensitivity analysis, which now shows that the main uncertainty remaining is in that well depth for RO2. But then that's highly correlated with the transition state 2. Probably if we wanted to better constrain the model further to better than a factor of 2, then we would need to carry out experiments at different conditions. So maybe higher pressures, temperatures, to better constrain this well depth. Okay, so hopefully the message is getting across, and what I'm trying to say is that by coupling theory and experiment together, we can do quite well for larger systems where we're not able to achieve the level of theory that we can achieve for the hydrogen-oxygen system, for example. Okay, so we can't, from using a priori methods, you know, Steve Klippenstein might get, you know, a really accurate prediction for parameters with, you know, a small number of atoms, but we can't easily do that for larger molecules. And so combining theory and experiment is a probable way forward to being able to do better for those larger molecules. So going back to what I was saying yesterday, that basically models are useful really if we can use them to extrapolate, to tell us things we don't know. And I think that combining experimental data with master equation modeling does allow us to extrapolate. So we're doing experiments, conditions that are miles away from our combustion modeling that we want to do, but by using a model and constraining the parameters within that model that are not sensitive to thermodynamic conditions, we can use that model to extrapolate to the pressures and temperatures that we're interested in. So I guess this is another case really of the sort of multi-scale informatics. I mean, don't know. We didn't come up with the terminology, but it sits into that same framework of combining information to give us better constraints for our system. Okay, so final remarks for today. So high-level theory, I think, is playing an increasingly important role in predicting rate constants that we can use in our combustion models. And, you know, better computer resources and better model descriptions of our systems are giving us uncertainties that are reducing rapidly over the years, really. But for larger molecules, you know, we've still got limitations on CPU power. And so we've still got uncertainties remaining from using theory in an a priori way. But using theoretical models and master equation modeling does allow us to make predictions over any temperature and pressure conditions that we might want to use. And so it's very flexible in that way. And so if we've got a robust model, we can extrapolate to give us data where we need it. And what I've been trying to show is that combining theory and experiment can help us to extrapolate. I mean, in the examples I've just shown here today, what we've been combining is kinetics experiments, so experiments that are designed to isolate specific reactions with our master equation modeling. I mean, in the wider sense of optimization, which I will talk about later in the week, we might want to throw all data at these systems, so maybe bulk experiments on flame speeds, on ignition delay times, on concentrations, plus theory, plus kinetics experiments, just throw it all together and optimize our system. And that, you know, that's also possible. So we'll come on to that later in the week. But I think that's where I'm going to end for today.